Alright, so the first thing that we're going to look at here is displacement. We're going to define displacement as how far an object is moving from its starting position. In other words, we're just talking about its change in position. Displacement is going to be represented by the letter D, and the units of displacement in physics are going to be meters. If for some reason we're given a unit that is not meters, like say centimeters or feet or inches, we're going to have to convert that over to meters. The last thing we want to know about displacement is how to realize when a question is asking us for displacement. And a key word or phrase that we're going to look for is how far did that object go? So for instance, if I asked how far did Mr. Weiss drive to school, I'm asking about his displacement. Another example might be how far did the plane travel on the runway? Or how far did the kid walk to school? Now let's take a look at velocity. Velocity is going to ask us how fast something is moving. So the definition of velocity is going to be the change in position over time. If we think about what this means, it's actually telling us that every second we're changing our position. So every second we're moving a certain amount of meters. The symbol for velocity is just going to be the letter V. Since velocity is telling us the change in position over time, it's going to have the units of meters over seconds, or meters per second. If we're given a velocity in miles per hour, we're going to need to convert that into meters per second. When we say the change in something, we're really referring to the slope of something. Our key word or phrase is how fast did that object go? For example, if I asked how fast was that car traveling, I'm asking you to tell me its velocity. Another example would be how fast did Mr. Weiss serve that tennis ball? I'm asking you to tell me its velocity. We all know that you can't calculate it because it's just that fast, but if hypothetically we were able to, we would know that I'm just asking you to find out the velocity. The next variable we want to look at is time. When we say time, we're asking how long it takes an object to do something. The symbol for time is just a lowercase t, and the units for time are just seconds. If we're given time in minutes or hours, we're going to need to convert that into seconds. Whenever we're asked how long did it take, that's just asking us the amount of time needed for that event to occur. For example, if I asked, how long is a class period? Well, that's just asking me how much time is in a class period. And right now a class period is 40 minutes. But don't forget, this is physics, so I'd have to convert that over to seconds. Another example could be, how long is this note video? Well, we'd have to look at the time to figure out how long it might be. And unfortunately, it is forever. It's never going to end. Now let's talk about acceleration. The definition of acceleration is the change in velocity over time. In other words, it's just telling us how quickly can we change our speed. So can we speed up? Can we slow down? How quickly is that occurring? The symbol for acceleration is just a lowercase a. The units of measurement are just meters per second squared. The reason being, acceleration is the change in velocity over time. Velocity has the units of meters per second, time has the units of seconds, so meters per second divided by seconds gives us meters per second squared. Now we're going to take a look at a position time graph. There's two very important things that we want to know when looking at a position time graph. The first being the y-intercept. The y-intercept of any graph is going to tell us the initial condition. In this specific problem, it's going to tell us the starting position of an object. The next thing we want to note about a position time graph is what the slope is telling us. The slope is telling us the change in position over the change in time. Well, we just said a few slides back that is actually our velocity. If we pause for a second and think about that, we're going to notice that a big change in position over a small change in time is going to result in a very big slope. A big slope is going to mean a big velocity. On the flip side, a small change in position over a big change in time is going to mean a small slope, and a tiny velocity. It's important to note that by finding out the slope of a position versus time graph, we can actually use that information to construct a velocity versus time graph. There's two very important things that we want to know when looking at a velocity time graph. The first thing we want to pay attention to is the y-intercept. The y-intercept of a velocity time graph is going to tell us our initial velocity, or the starting velocity of that object. The next thing we want to pay attention to is the slope. We'll notice that the slope of a velocity time graph actually gives us the acceleration. We said before that acceleration is the change in velocity over the change in time, which makes sense why the slope of a velocity time graph is acceleration. The last thing I want to talk about is the meaning of the area under the curve. The area under the curve of a velocity time graph will tell us the total displacement of the object. In other words, the change in distance, meaning the final distance minus the initial distance. Alright guys, let's get started with our position versus time graphs. And these notes are going to be about understanding the motion of position graphs. Whenever we're looking at a graph, we want to be able to understand what is it telling us. And something really important about this graph is its slope and what it means. We know that slope is just the change in y over the change in x. And for this graph, that would be meters over seconds, meaning meters per second. And we know that meters per second are the units of velocity. Let's take a look at our first example, which will be a straight upward slope line. Because the line is straight, it means that it has a constant slope everywhere, which means that it's going to have a constant velocity everywhere. We can also see that our line is starting at 0 meters, or the bottom of the y-axis, and ending at the top of the y-axis, so some positive meters later. This means that we're moving away from the origin. Let's take a look at the opposite now. Now we have a straight downward slope line. Because it's a straight line, it still has a constant slope, which means it still has a constant velocity. We also see that we're starting at some positive distance and ending at a distance of 0. This means that we're moving towards the origin because our overall distance is decreasing as time increases. Summarizing what we just talked about, we can classify distance increasing as a wave. In other words, when our distance approaches infinity or moves away from 0, that means that our object is moving away from the origin. Oppositely, when our distance decreases or our distance is getting closer and closer to 0, we can classify that as moving towards the origin. The origin is just the place where distance is equal to 0 meters. When looking at a motion graph, that would be where the y and x axes intercept, meaning that y is equal to 0 meters. Now let's take a look at another straight line that's neither sloped up or sloped down. We'll notice that we have a horizontal line, and the slope of a horizontal line is just 0. Since slope is velocity, that means that our velocity is 0 meters per second. If we don't have any velocity, that just means that we're standing still or stopped. Another way to describe it is saying that we are at rest. We need to notice though that our distance isn't 0, which means that we're actually starting away from the origin here. Now let's take a look at another line, but this time it's going to be curved. Since this line is curved, the slope is changing everywhere on this line. And since we have a changing slope, that means that we have a changing velocity, which means in other words that our velocity is non-constant. A changing velocity means that we are experiencing acceleration. We would say that the motion of this line is speeding up because the slope is getting steeper and steeper as time goes on. This makes sense because we said that velocity is the slope. If the slope is changing but getting steeper and steeper, that means that our velocity is getting faster and faster. If our velocity is getting faster and faster, it means that we must be speeding up. Because our line is moving upward, it means that our distance is increasing. Therefore, we are moving away from the origin. Let's take a look at another example here with another curved line. Here we have a curved line that is also moving upward. Again, since this is a curved line, it means that it has a non-constant velocity, which means that it's experiencing some sort of acceleration. In this case, the slope is getting less and less steep, which means that our velocity is getting slower and slower. Therefore, I would say that this line is slowing down. Again, because this line is moving upward, it means that we're moving away from the origin because our distance is increasing. Now we're going to look at another curved line, except this time it's going to be moving downward. Because this line is curved, we know that it has a non-constant velocity. We can look at the slope and see that the slope is getting steeper and steeper as time goes on, which means again that we are speeding up. Because this line is moving downward, or in other words, its distance is getting smaller and smaller or closer to zero, it means that we're moving towards the origin. We got one more example left. And that's going to be another curved line that's moving downward. I know I've said this 3 times, but I'm just going to keep saying it. Because it's curved, it means that we have a non-constant velocity. And because it's a non-constant velocity, it means that it's experiencing acceleration. In this case, our slope is getting less and less steep, which means that we are slowing down. We also can see that our line is moving downward, which means that we're moving towards the origin, because our distance is decreasing. Let's summarize everything that we just talked about. When looking at a position versus time graph, a straight line is going to give us a constant slope, and a constant slope is going to mean a constant velocity. A curved line is going to give us a non-constant slope, or in other words, a changing velocity, and that's going to result in the object accelerating. And acceleration can be defined as either speeding up or slowing down. Let's quickly talk about how we can identify when that curved line is either speeding up or slowing down. As we mentioned before, slope will give us the velocity. So that means that if slope is getting steeper and steeper, that means that our velocity is getting faster and faster, which means that we are speeding up, and it's going to look something like this. On the flip side, when the curve is getting less steep, our velocity is getting slower and slower and slower, meaning that our curve is flattening out towards the end. Which makes sense because a flat or horizontal line has a slope of 0, meaning a velocity of 0. Which means that if our curved line is ending in a horizontal line, we are ending at a very, very slow velocity, meaning that we must be slowing down. Lastly, when the line is moving towards the x-axis, meaning that our distance is getting closer and closer to 0, we are moving towards the origin. On the flip side, when the line moves away from the x-axis, meaning that distance is approaching infinity or moving away from 0, we are moving away from the origin.